now. All right, so we are recording. Today's lecture is going to be about set notations. I hope you guys had a chance to at least review all the Boolean operators because we're going to use those operators today. Um, and we're going to build new concepts on top of what we have learned last Wednesday. So, do we have any questions about the Boolean operators that we talked about last week before we proceed? No questions? All right, very good. So just to let you guys know, this is just a reminder for people who were here on last Wednesday, sign in to Canvas, so that we can take role efficiently when I get you guys, the role taking activity. Okay, because this way we don't have to kind of struggle to sign in or have difficulties at that time. All right, so this is the module from last time, and how many people try to use Gemini to kind of review the concepts, or kind of get yourself some quizzes just to make sure that you're understanding the notations and whatnot? Not yet. Okay, that's fine. I can see that it may not be necessary yet, but after today, I think that's going to change. Okay. Yes. Hmm? Oh, you just missed the deadline. I can do that. Give you guys just a little bit more time. All right. So what he was talking about is the co-requisite checking. It's not really an assignment. It's just you guys to turn in something so I can check whether you have met the prerequisite or co-requisite, your prerequisite or co-requisite requirements. All right, so I think it is this one, and I can give you guys just a little bit more time. Okay, we'll make it a 30. So it is important to make sure that you get all the email regarding announcements and whatnot, because that's how I can communicate with you outside of class time. There we go. All right. I also updated the syllabus in terms of my um, office hours. I have changed that. So in case you need to contact me or come see me, this is the old one. The new one. Oh, why is it not changing? Darn it. Okay, so the new one is actually um, this is actually partially correct, but it's not. Oh, this is what about the class. Okay, never mind. Looking at the wrong piece of information here. So office hours have changed. For this class, the office hour is immediately before the class meeting. So that means if you need to talk to me, just kind of come to my office before class. Um, and hopefully that is convenient to most of you. I'm usually available after class as well. Okay, so if you need to talk to me, you can also wait until the class is over. Today is kind of the exception to the rule. I actually got something to do after class, so I will have like maybe about 15 minutes after class today, but normally it is fairly open. So, do we have any questions about the office hour change? Nope, no questions. All right. So if there are no questions, I'm going to close the syllabus and we are going to move on to, um, okay, this is not the tab. This is not the tab. Nope, nope. Hmm. Okay, I wonder where that tab went. That's okay. I can always reopen it. All right, so we are moving on from the Boolean operators, which is what we talked about last Wednesday, to this particular note here. So when you see something with a title like that, okay, a more hair splitting mathematical way to define set notations, what comes up in your mind? Yep, yes. Do you think it will take you some time to understand it, or do you think this is like, oh, I can get this, no, no problem. It's gonna take you some time, okay, because it is abstract, okay. So that's why it is important to read ahead of the class, okay? Because if you did read ahead of the class, then you know at least what I'm going to be talking about, and you might, also have some idea of, if you have questions to ask in the class. All right. And you can also see that it has some quote unquote prerequisites. It's not actual prerequisites. I'm not going to check, okay? But it does rely on Boolean operators, which means, if somebody is still, having some problems about the notations of the Boolean operators, this will be difficult to understand, okay? Because I'm relying on you guys to have studied and understood the material from the previous class in order to move on to the following class. Okay, so that is a really important thing to do. The second one is the syntax to describe syntax is not 100% necessary. Okay, we only got one little place where it is relevant, but it talks about B and F. Okay, how many people have heard about B and F? Which is a meta syntax. It is a syntax to describe syntax. Nobody. Then how did you learn C++? Okay, I hate to say it, okay, but I'm suspecting many of you use trial and error. Okay, you learn by examples. Okay, you look at a bunch of programs, you go like, okay, from reading these programs, I can kind of generalize the rules. And if you make a mistake and the rule that you understand is incorrect, then the compiler is going to bark at you and go like, nope, this is not going to work. Is that kind of how you learn the syntax of C++? Kind of? Okay, so I'm going to suggest a slightly more effective way, at least for some people, to learn the syntax of a language. Why do you think that is important? Well, if I know C++ already, there's nothing else I need to learn ever anymore. Would that be a relevant or correct assumption? Nope. How about, well, because AI is getting so smart, I don't need to write my programs anymore. I just need to use, somewhat grammatically correct English to describe what the program needs to do, and I'll just let I do the rest. How about that assumption? Okay, you guys are turning your head. Okay, I think that's good. Okay, that's healthy. Because, if AI can do just that, then the CEOs don't need you anymore. All they need to do is to describe this is the next product that I need to make. And just describe it. They don't need software engineers whatsoever. Okay. They will also tell the AI to test the code. They don't need test engineers anymore. Okay. So we certainly do not want AI to be able to do all of that because if AI can do all of that, you won't have a job to pay off your student loan. Okay, that's gonna hurt. Okay, if you have a student loan and you have to pay it off and you cannot land a job that you originally planned, that will hurt. Some people have found that out already. Okay, a lot of people were laid off in the past few years, and many of those people have to struggle to pay off their student loan. So I certainly do not want any one of you to end up in that situation. All right, so moving on. And the third prerequisite is a general understanding and the ability to differentiate the following words slash phrases. So can everybody understand the difference between all versus every? When to use and all and every are the same, but then the next one, which is at least one, is different. So does everybody understand when to use every and when to use at least one? Okay. Such as tech always starts a class, okay? Every class, tech starts with some kind of nagging as if he is my parent. That is a good use of every, okay? What about at least one? Can someone give me an example of when to use at least one? You have at least one pencil, okay? In order to take notes, you need at least one way of writing, okay, which is also a good reminder, okay, that's another example of me nagging, okay, because taking notes or at least having a way to take notes when you need to take notes is important, okay, except for people who have already gotten a computer science degree somewhere else and just need to officially get a degree in the United States, but they got everything already understood. Okay, so except for those people, for probably very few, um, being able to take notes is important. Okay, very good. All right, so we are moving on to the abstract stuff now. Okay, so this is a notation. I put boxes around certain types of expressions because it is the focus that I need you to kind of, well, it is the focus of that particular bullet point. And so in this case, the symbol, let me use the mouse pointer, this little symbol here that looks like an uppercase E but with round edges, it is called element of, okay? Or if you prefer, it is also in, that's also another way to call that operator. So in this case, A, which is just some kind of random value, is in, okay? In this case, X, which is uppercase, is a set, okay? In other words, there, given any particular value, given a particular set, it's either the value, which is A, is either in or it is not in a set. Is that okay? So this is an expression, it's a Boolean expression, which means it returns a value that is either true or false. Okay, so that means, it is not telling you that A really is in X. It is asking the question, is it true or is it false that A as a value is in a set X? Are we good with that concept? Okay, we're good. All right. Now, I think I have talked about this last time, but since at least two of you were not in the lecture last Wednesday, it is really important to take notes and also, to put all the definitions in one particular place. Because this way, when you need to look up the definition of the symbols or the operators, you just have to go to one place. Just because it is in my lecture notes or the reading module does not mean it is easy for you to find. The key is you want it to be easy for you to find because your exams are open book and open notes. So when you are taking the class, you also want to be preparing for your study guide for the exams. Okay, so that's why it is also important to take notes and keep it organized. So I try to break things down into concepts. Okay, so this is a concept of element of. It is an operator that returns a Boolean value. Um, it is a foundational concept. So this is describing, how is it a high level concept or low level concept? This one is foundational. All of the other set notations depend on this particular concept. So in this case, this is an example. One is in what looks like a funny looking Z. The funny looking Z is the set of all integers. So if I ask you, is it true or is it not true that one is in the set of all integers? The answer is yes. Okay, because by its very definition, the set of all integers include or contains all the integers. Okay. On the other hand, 1.25, which is not an integer, is in Z. That Boolean expression is false. Okay, so let me point to the second expression here. 1.25 is in Z, which is the set of all integers, is false. Do we have any questions about the notation? A is in X, whereas in this case, A is just a placeholder for a particular value, X is just a placeholder for a particular set. Do we have any questions? No questions? All right. Yes, go ahead. In Yeah, in this class, I don't use it, but in mathematical notation, yes, there is a symbol, which is the same thing as element of, but with a strike through. So if you see a strike through, okay, I can just write this on the whiteboard because I'm not going to use it. So there's a symbol called like this. Okay, that means something is not in something else. So that means A is not in X means exactly the same thing as the negation of A is in X. So the 3 bar means equivalent to, which means one side is true when the other side is true, only if the other side is true. But for this class, because we have already talked about if and only if, we can actually just use the symbol if and only if in this case. Are we okay so far? So this particular if and only if is only used to define this particular operator, assuming that we already understand the element of operator. So that's a good point, okay? Because some of you probably have to read certain types of math proof where they make use of this particular symbol. It just means the negation of element of. All right. So very good. Next one is pretty easy. A equals to B means the value of A and the value of B are the same, and therefore they are interchangeable. So the concept of is really just, equal to, which you all understand already. And just a quick check, what is the C++ symbol for equal to? Double equal to, very good. Okay. What about JavaScript? Double or triple, very good. Okay, so double is can be type coercing, which means if the types of the two sides of the double equal are different, then JavaScript will try to match them. But in the process of matching, it may or may not do what you want it to do. Triple equal in JavaScript is basically saying they have to be exactly the same type and the same value. Okay, so very good. I'm glad that you know that already. Cool. Well, JavaScript by itself is pretty cool. Yeah, it is really good because you can do client-side scripting, you can do server-side scripting, you can also do Google Apps script programming. So all the if you have a Google Sheets, the back end of Google Sheets is programmable using Gas, which is basically a form of JavaScript. Yeah, so it's super duper helpful in that case. hmm Yep. Yeah, I would say JavaScript is probably as practical and useful as Python, but it kind of depends on what you want to do. Yeah, if you want to do mostly AI stuff, then Python is probably a little bit more useful. But generally speaking, JavaScript is a good language to learn. All right, very good. All right, so here's an example. I don't think anyone's going to complain about this. 2 divided by 2 is the same as 2 minus 1. Okay. All right, so the third one is the concept of a predicate. So it's a fancy name, okay, predicate. So in this case, I'm just using uppercase P as the name of the predicate, and A, lowercase a, is the parameter to the predicate. You can just look at it as a function, okay? Just think of P of A as a function that returns a Boolean, which means it can only be true or false, and in this case, A is the parameter. Um, so the actual definition of PA kind of depends on the context. So in this case, the concept is fairly simple. It relates to CISP even 360 really well because a predicate is a function and it has a type of a Boolean. Now, it doesn't always have just one parameter. It kind of depends on what you want the predicate to do. Sometimes it can have no parameter, okay? It just returns either true or false all the time, or otherwise you can have many other parameters. Kind of depends on the context. This is an abstraction notation, so that this way I can make use of the predicate instead of having to plug in an actual expression. Okay, so that's the whole purpose of introducing the concept of a predicate is so that it can serve as a placeholder of an expression that returns either true or false. So here's an example. So the example is I can define p of x to be x mod 2 equals to 0. Then p of 1 is going to return false, while p of 24 is going to return true. Do we have any questions about the example? Does everybody remember what is mod or module? Okay, very good. Shall we move on to the next one, the funky looking inverted A symbol? Are we good? Are we ready to move on? All right. So the inverted A symbol means it is called a universally quantified, it's called a universal quantifier. So in this case, we are basically saying for every E in the entire universe, P of E is true. Okay. Or the other way, the correct way of saying this is to say this expression is true if and only if every single thing in the entire universe will make the predicate P true. So are we okay with that concept? It doesn't sound like really helpful, right? Because most of the time we just want to limit our scope to a particular subset of all the things in the universe, but there's a way to do it. Okay, the example actually illustrates that perfectly. But without knowing what P of E is, this is applying to everything in the universe. So it applies to every integer, it applies to every real number, it applies to every irrational number, it applies to every complex number, it applies to every vector, it applies to every matrix, and so on and so forth. Okay, which means by itself doesn't seem very useful. Okay, but what the way you formulate the predicate P of E is what makes it useful. All right, so now we are going to, this is the symbol. So we're going to go through the example here, and we will try to say whether that is uh, the quantified expression is true or not. So when you only look at this part, okay, which is for all I in the entire universe, you go like, so can I be tech? Yes. Can I be Iraj? Yes. Can I be the STEM building? Yes. Okay. It is yes to everything in the entire universe. Okay. Can I be the planet Mars? Yes. Can I be a single air molecule on Mars? Yes, and so on. All right. So you go like, that is pretty useless, but the predicate that is inside, which is this part of the expression, makes it meaningful. Okay, because now we're asking, is that I an element of the set of all integers? So now you go like, oh, okay, now we are being a little bit more careful because if variable I is bound to tag, okay, am I an integer? Nope. What if I is bound to the value of 6? Yes, it is an integer. What if it is bound to negative 25? Yes, it is an integer, right? So that means, oh, okay, so now we are starting to we have a mechanism to be selective. So now we look at the implication. This is implication. And this is I is an element of R. So this is really asking if I is an element of the set of all integers, does it imply that I is also an element of the set of all real numbers? The answer is actually yes. So the quantified expression itself is true. Okay, the quantified expression, which is referring to the entire thing, has its own true false value. In this case, this particular quantified expression is true. No matter what you choose in the entire universe as the value of variable I, the expression inside the parentheses would still be true. Yes. It is hard to see it as a C function, um, because you will need a way to iterate through, all the possible values in I. So, and C++ is really poor in terms of, understanding the set notation. It just does not actually do it. Um, so it's pretty hard to have an equivalent understanding in C or C++. But um, I can probably explain it as a loop, okay, in a sense, okay. The loop is going to iterate through, so I is going to have to iterate through every single possible thing in the entire universe, okay. And then the loop is saying I need every iteration to return true. So for every iteration of that loop, it is evaluating what is inside the parentheses, okay? And it's ANDing, AND, is ANDing the result of every single one of those evaluation. So if the final evaluation, if the entire huge gigantic conjunction is true, then the quantified expression is true. So that's one way to kind of visualize it using a loop, but the concept itself, is not um, doesn't imply a control structure. Okay. Any other question? Parentheses. So the way it does, okay, so it goes back to this notation here. So we usually have something to say about, the universally quantifier. So in this case, this is a placeholder, right? So P of E is just a placeholder in this case. So in this case, you can look at this as P of I. So we are just defining, what the predicate is that we want to evaluate. The upside down A, this one and this one. You mean the element of? This is a temporary variable. So it is kind of like, okay, so if we want to coerce this into C++ concept, it is kind of saying, for, okay, so I'm going to use, the previous example, the E, okay. So this is kind of like, object, because we don't even know what the type is. I cannot say int, okay. So for object E, um, and I don't know how to initialize it because there's no way. So we'll just say for object E, I need to express, in, okay, we'll do it in universe, okay, because everything is in the universe, okay. So what we are really trying to do is to say this is the true false value of the entire expression. We'll call it V. So V is initialized to true, and then inside the loop here, we'll just say that V equals to V and P of E, close loop. So V is the value of the entire quantified expression. Is that okay? Okay. So that's the best I can do, just borrowing the syntax of C++. But the key is V is initialized to true, and we are connecting all the sub-expressions using a conjunction. Now P can be anything. Okay, P is really just a placeholder of okay, what Boolean expression do we want to evaluate for each thing in the universe? That's what P is trying to do. All right, are we good so far? All right. So now that we have an understanding of the universal quantifier, which is the inverted A, and you can remember that by saying, it all starts with an A. Okay, because this symbol is also known as for all. So you can look at this symbol and just equate it to the phrase of for each, for every, for all. Are we good so far? Sometimes it helps you to kind of map these mathematical symbol to a phrase that you already understand. So what about the next one then? The next one looks like an E, so you can relate it to exists or there exists. Okay, so the term there exists in mathematics is really just a fancy way of saying at least one. So now it means there's at least one value E in the entire universe. Okay, so the quantified expression. Okay, let me use a mouse pointer. This quantified expression is true if and only if there's at least one thing in the entire universe such that P of E is true. Once again, P is just a placeholder, so I can describe the expression, the Boolean expression that we need to evaluate. Are we good so far? And this is called the existential quantifier, which because we just need there's only one thing, okay, at least one thing in the entire universe that can make P of E true, then the entire quantified expression is going to be true. Are we good so far? All right. So assuming, because nobody asked, assuming we understand this code earlier, I am going to overlay the version for the existential quantifier. Okay, so I'm going to use a different color, so this way you can tell which one is for which one. So if we want to change this code to existential quantifier, then the true becomes false. We initialize v to false instead of true. The loop structure is still the same. We are still iterating through every single thing in the entire universe. The expression is also going to change. Instead of a and, it becomes a or. And that's it. So you can see how the universal quantifier is really a gigantic conjunction. The existential quantifier is really a gigantic disjunction. Yes. You can do that, but then you're going to have to use a break, right? I hate breaks. It is faster, but it also breaks a lot of code analysis approaches. So, breaks, continues, go tos, those are, and also returning in the middle of nowhere, those are all huge no-nos from my perspective. Now, I'm not going to grade your programs. Okay, this is not a programming class, so you guys are free to use whatever control structure that you want to use, including using just labels and go-tos, and totally do not use, anything that has structure in it. But as an example, okay, I just prefer not to use break. Now, if you don't want to use break, okay, and you want to be able to get exit earlier, um, this particular control structure cannot do it. But with a regular for loop, you can still do it because you can look at V as the middle expression. So in the conjunction, you can say, as soon as the V becomes false, exit the loop. So that becomes a part of the condition of the loop. With an or, you can also say, when V is true, then we exit the loop. In other words, you make it explicit to be a part of the condition that stays for you to stay in the loop. So this way you don't have to use break. Hmm? I do not like breaks. I try to program without breaks, continues or go tos. Now, throwing exceptions is a different thing because by the time you throw an exception, most of the time, not always, there's no way to recover. So you just throw an exception, and typically the program just quote unquote bomb out with a message. Okay, and that's the whole point is you don't just bomb out, it bombs out with a message. All right, so I think it is a good time to take row right now, and I'm going to release the row taking activity. So if you have signed in already, it's a good thing. Yep. What does Z mean? You mean this Z here? All right. Well, it's explained earlier. This is also why it is good to read the notes ahead of time. Jack, you don't have to rub it in. All right. So, oh, right. The road taking activity. There we go. So I just turned it on. You should be able to see 2016-0126 road taking. And the word or the access code is definitive. And you need to sign into the school network in order to get in because I did the IP filtering. So definitive is the word because that's what we are doing today. We are defining stuff. We're defining symbols. So I'm gonna give you guys maybe another minute or so because I cannot differentiate whether you're still doing it on your phone or whether you're texting someone. It's like this class is so boring. I'm dying with skulls, emoticons. Die, die, die. All right. All right. So I think most people were done, and I'm gonna proceed. We'll continue with the discussion. Yes. Say again. That's okay. I if I see a zero, okay, it means you did turn in something, or I can just make it a negative number of points. Nah, it'll be fine. Just send an email to remind me that I need to nudge your score. All right. So there exists existential quantifier. So this is an expression, okay, that has its own value of either true or false. And in this case, it is false. Okay, so let's check out why it is false. So it is saying, okay, if you just look at these two, it is saying for everything in the entire universe, okay, we need to evaluate the following. But I only need the parenthesized expression to be true for at least one of the things in the entire universe. So find me one thing that makes the expression inside the parentheses true, and we're good to go. Okay, we can conclude the entire quantified expression is true. Okay, so what am I looking for? I am looking for something that is an element of the set of all integers. So we're only limiting to integers. So this is how we can limit the scope of what we need is to use conjunction inside a existential quantifier, but we use implication inside a universal quantifier. So let me just do a quick check here, okay? Because I did that without remembering to check first. So in a universal, not yeah. So in the universal quantifier, using the implication, what happens when in that particular iteration of the loop, I is tag, okay? So tag is an integer is false. So what happens to the implication? The implication becomes true. That is correct. And how do we know that? The truth table from last Wednesday. That is correct. Okay. Yes, because you took CISP 310. There must be lectures where I spoke, truth table at least 20 times within a lecture. Yep, exactly. All right. So in this case, it is a conjunction, which means we need all three expressions to be true at the same time. So I'm looking for something that is an integer. I'm looking for something that is also greater than zero. And I'm also looking for something that is less than one. Then you guys go like, that's easy. Zero point 0.5, right? But zero point 0.5 is not an integer. There's no integer between 0 and 1 exclusively. So that's why, oh, there's nothing. Okay, I cannot be anything in the entire universe where the parenthesized expression is true. So that's why the existentially quantified expression is also false. Are we good with that concept? Okay, all right. So now that we have introduced quantifiers, we have Boolean expressions. Now we can define actual set operators. Okay, this is the first one. This is called the intersection. Okay, so that means how do we define the membership of an intersection? Something, okay, of the entire universe. Something is in the intersection if and only if that something is in X and that something is also in Y. That is the actual definition of intersection. Are we okay so far with the concept of intersection using just the symbols that we have seen so far? So in this particular case, um, this box here is telling you what I'm trying to define. I'm trying to define this funky inverted U symbol using things that we have learned already. I'm using the universal quantifier. I'm using the element of operator. I'm using if and only if. I'm using conjunction. So that is why it is crucial in this class to make sure that you understand all the concepts either before a particular class or even at an earlier part of the same class. The moment you go like, I'm not really sure what that means, you need to raise your hand and let me know. Yes. Okay. Well, the reason why I gave you that phase is because okay, so there's a narrow scope to that answer, and there's a wider scope to that answer. The narrow scope to the answer is um I'm what I'm trying to do is to use only symbols to define more symbols. Okay. Um, the reason why I want to do it that way is because that mathematics is a language. Okay, it's not a programming language, but nonetheless, it is a language. So why do we have mathematics as a language? In other words, these symbols existed long before the first computer was invented. So why do we have mathematical symbols? We kind of talked about it last Wednesday a little bit. I'll see. I'm checking to see if you guys remember. Yep. Okay, so there's the conciseness, right? There's the conciseness of mathematical symbols, but there's one more thing that is actually really important with mathematical symbol. Precision, exactly. Okay, it is precision. There are no two ways to interpret exactly the same expression in mathematics. But in normal English, okay, because we don't typically use parentheses, so there are times where we don't know, which two things are related first, and then that concept is by itself related to the third thing. So we kind of have to use we can use common sense, okay? In normal life, we can use common sense, but in when we are talking about something like this, there's no quote unquote common sense to talk about. Okay, so that's why I want to use the most precise language to define something. Okay, so getting back to your question, the other way to look at this for people who are more kind of visual is to use what we call a Venn diagram. Okay, so Venn diagram, not Vern. So a Venn diagram is basically saying um, you can look at the inside of this circle as elements of X, and then you can look at the what is inside the second circle to be elements of y. So this is a really typical, Venn diagram. So the intersection is this portion here because they are in X, but they're also in Y at the same time. So I can just kind of comment here, okay? So I will use this kind of green color thing, color code this, and call this X intersecting with Y. In other words, X intersecting with Y is its own set. Are we good so far? All right. Do we have any questions about the concept of intersection? I'll go through some examples later, but first of all, I just want to see if there are any questions regarding the definition itself. Yep. Yeah, we'll talk about the empty set later because there is such a thing called an empty set, okay, which is it's still a container. It is still a bag, okay, except there's nothing inside the bag, but the bag itself exists. Yep. All right. So the next concept is called a union. So we're moving on to the concept of a union. This is the concept of a union. So when you look at the definition of intersection and the definition of union, you go like, they're almost exactly the same. That is correct. They're almost exactly the same because one makes use of conjunction, the other one makes use of disjunction. Okay. So now, what does it look like in this picture here? So if the green portion is X intersecting with Y, then the blue portion, which is a kind of weird shape here, okay? So everything inside the blue portion is X union Y. Is that okay? Because X union Y means, okay, everything that is in X or in Y is in the union. But in this case, the or is not exclusive. Okay. In other words, things that are in both in X and Y, which is the green portion, they're also a part of the union. So the union between two sets is guaranteed to have everything in the intersection. Yes, there is one limitation, which is you can only each value can only appear once as an element. So you cannot have repetition of elements in a set. Yep. So that is correct. Yep. So we have some examples later on, and I think we can probably get to those today. hmm All right. So the next one is difference. Okay. X minus y. So the definition of x quote unquote minus y is it has to be in x, but it cannot be in y. Okay. So once again, I'm using mathematical symbols here, which means either you have studied this and you feel comfortable with the math symbols, or you have a little lookup table somewhere in your notes. So when you see something like this, you look it up quickly. You go like, oh, that's just and. When you see something like this, you look it up, and it means or, it means not. Okay, so you kind of have to keep up with this class using either a quick lookup, or you just study it so that you already understand it. All right. So what about in this picture? What is x minus y then? Let me see if I can find a red one. Yep, here's a red. Oh, I actually got one in under my monitor. So x minus y is everything that is in x but not in y, right? So that means the red portion, which is representing everything in x, is still here, but it cannot be in y. So the red portion here is x minus y. Are we good so far with the concept of quote unquote subtraction? It looks like subtraction, but it's not exactly subtraction. Okay, we're looking at everything that is everything that is in X but not in Y. Are we okay so far? Any questions? Upside down U? You mean this one? Yep. All right. Well, I think we can probably go for a few examples before moving on. So let me just kind of scroll to the example portion. All right. So here is ABC intersect DAC, and the answer is CA. So the way we list elements inside a set is not order dependent. There's no intrinsic ordering within a set. So in this case, if I want to spell out the first set as ABC, okay, that's cool. If I want to spell it as CBA, that's fine too. They are exactly the same set. It is not ordered within a set. Unlike in an array, everything is ordered. Okay. So the second set has the same element A, also has the same element C. So that's why the intersection is the set CA. In the second one, we are looking at union. So this time, we cannot have duplicate elements. So even though A is on the left-hand side, A is also on the right-hand side, but in the union, it only appears once because we cannot have duplicate values in a set. Are we okay so far? All right. The third one, I'm not sure why it just kind of looks kind of funky. I think it has to do with my browser. So on the third one, we are looking at everything that is in the first set, but not in the second set. So in this case, A is in the first one, but it's also in the second one. C is in the first one, but also in the second one. So B is the only element in the first set, the left-hand side, but not in the second set. So that's why B is the answer in this case. All right. So we'll talk about the empty set in just a little bit. So I'm going to go back, to continue the discussion before we move on to talk about the empty set, which is kind of really close. All right. So this particular symbol here is called subset of. Okay. So when you look at the rectangle portion, that means x is a subset of y, and the reason why it is kind of rectangle is because that's the symbol that we are trying to define. So we basically say x is a subset of y if and only if for all e is in x implies e is in y. That's how I would spell out this entire expression. Let me say that one more time. This is basically saying we're defining the subset of operator. We say that x is a subset of y if and only if for every E in the entire universe, E is in X implies E is in Y. Yep. Yes. In order for subset of to be true. But X does not have to be a smaller one. It can be exactly the same size as Y. Yep. All right. And then the next one, this one looks exactly the same thing as subset of, except the little bar that is underneath is gone. So this one is called a proper subset. So we say that X is a proper subset of Y if and only if, and we make use of the first definition, we say that X is a proper subset of Y if and only if X is a subset of Y and there is something that is in Y but not in X. In other words, X has to be quote unquote smaller than Y. There has to be at least one thing that is not in X but in Y. So we'll take a look at some examples. I'm just going through this, until at least I can get to the curly brace, notation. So we are just kind of we're getting there. Let me just skip this one over until, and then we'll get back to it later. All right. So this is the part where I make use of BNF, and I cannot remember the full name of BNF. BNF in computer science. It's the first name of its Bacchus Nor form. You can see that it's in Wikipedia, which means I did not invent it, and I did not write this article either. Because you can always say, but Tech, you can always kind of make up something, put an entry into Wikipedia, and call it a day. Nope, nope, this is actually real. Okay, so BNF is a meta syntax, which means it is a syntax to describe syntax. In this case, the meta syntax is actually pretty easy to understand, unlike the meta syntax of C++, which is a huge, gigantic mess. So we'll go back and look at the actual BNF in this case. So the BNF of a set notation, in order to list members inside a set, we have boldface braces on the outside, and then we have not boldface square brackets, and then we have element, which is italic, and then we have not boldface braces here. We have comma, which is actually boldface. It's hard to see, but it is boldface. And then we have this little asterisk here. They all mean something. Okay, so I'm going to go through each one, one by one. Everything that is boldface is called a terminal, which means in the actual instance, okay, it has to be there. Syntactically, the outside curly braces or the outside braces, they need to be here. Okay. If you want to separate an element from another element, the comma has to be there. Okay. So everything that is boldface is basically verbatim. Okay. They are called terminals. Yeah. Yep. That's all right. Yeah. The comma is bolded. Everything that is italic is called a token. It is basically just a placeholder of something else. Everything that is between not bold square bracket is optional. Oh, so tech. Sorry. Go ahead. Oh, okay. That's all right. Not a problem. So the square bracket here means, oh, this entire thing is optional, which means I can start with a brace and end with the close brace and call it a set. That is called the empty set. It has no elements. Is that okay? Yep. Well, JSON is using, they are using the braces, for objects. So yeah, there are only so many symbols on the keyboard. Okay, so everything that is between braces is a group. So that means, this whole thing, the comma, which is a terminal, and the element, which is a token, is combined with those two things. It is grouped, okay, using the not both face braces. Okay, so why do we want to group? Because we want to apply the asterisk to the entire group. So the asterisk means whatever is immediately preceding the asterisk can be repeated any number of times, including 0. Okay, so this is the BNF of how we list the membership of a set that has a finite number of elements. So let's go ahead and check how we understand the concept here. All right, so I hmm? Comma is a separator of one element from the next. So first of all, is this proper syntax? Do you think the syntax description will say, yeah, it meets all the rules? It does meet all the rules, right? Because it starts with a brace, which is boldface. It skips everything in the middle because the square bracket says it's optional. It ends with a close brace. Okay, it meets the rule. Okay, so this is called the empty set, but it is a set. Okay, so we're gonna look at a set of just one single element. Okay, so in this case, does it meet all the rules? It opens with a brace, okay, matching this boldface with a brace here, but this time the optional part is actually here. So what does the optional part says? Well, we have to start with at least one element, right? Tag is one element. Okay, so tag matches this token here, but this portion here can occur any number of times, including zero. So in this case, this portion, the portion inside the not boldface braces, is repeated zero times. So that means, oh, okay, that meets that requirement. Okay, not a problem. So now we take a look at tag, comma, Iraj. Oops. Uh, J. There we go. Okay. So does it meet all the rules? So we have the open brace. We have one element, right? And then we look at the comma combined with Iraj as the subgroup inside the braces over here. And this time it occurs exactly once. So does exactly once meet the definition of any number of times, including zero? Yep. So this is all good too. So are we starting to understand, the description of syntax? Okay. Um, Depending on what you will be doing, um, by the way, this is actually pretty simple BNF. It belongs to a special class of syntax called regular expressions. Has anyone heard about regular expression as a term? Okay. How do you use regular expression? That's okay. It is a description of um, a language. So, and it's using the same kind of, a similar kind of notation. In fact, the actual regular expression of VI and also JavaScript and also Perl and also PHP and also Python is actually influenced mostly using the same kind of symbol. Not exactly the same, but very similar. And being able to use regular expression is actually really helpful. Let's just say that you want to find all the function calls with a certain property, like, there are like only two parameters instead of three because the third one is optional. Okay, you can actually write a regular expression to locate all the occurrences of the function call that's only making use of two parameters and not three. Okay. Um, you can also use combined regular expression with substitution with your fancy editors like VI. Now, I call VI a fancy editor just because most people do not like to use it. But in terms of the heritage, VI is really old. I'm thinking it's a product from the late 80s. Okay, but it has regular expression. It also has substitution. So you can actually write a single expression and say, run this for me. And it can exchange parameters. Now, that expression is going to be kind of ugly looking, but you can do it. Okay, it can do a lot of things. So anyway, given the syntax described, the ordering of elements in this notation is not important. So these are all basically specifying exactly the same set, and there are exactly 6 ways to do it. Because when you look at A, B, C, there are 3 elements. The number of ways we can choose the first element is 3, and then that leaves 2 ways to choose the second element. So 3 times 2 is 6. But once you fix the first 2 elements, the third element is already decided. So there's only one option. So it's 3 times 2 times 1, which is also known as 3 factorial. Okay, so these are the 6 possible ways to write exactly the same set. They are equivalent to each other because ordering is not important inside a set. Is that okay? All right. So with that knowledge, okay, now that we understand how to read a set, which I've been using a little bit implicitly, so now we have this intersection here, ABC, which is a set with 3 elements. The intersection between ABC and the empty set is just the empty set. In other words, I'm asking, what is in the set of ABC and also in the set of an empty set? Go like, nothing. Yep. If I understand it, you can do it. Yep. So I do understand the other symbol for an empty set, but to be consistent in this class, I just use open close brace to represent empty set. But you can use the other one as long as you. Okay, in an exam, you probably want to ask me first, and say, okay, I'm using this to represent the empty set. Is it okay? Just in case I'm not familiar with a particular symbol. All right. The union, okay, so ABC union empty set is just the original set itself because you're asking what is in the left-hand side and or the left-hand side. Excuse me, the other way. What is in the left-hand side or the right-hand side? And it will be, oh, because the second one is empty, so that means everything in the on the left-hand side is the actual set that we are talking about. Um, all right. Subtraction is a little bit interesting here. Okay, does everybody see why the empty set minus any set is the empty set itself? Because I'm asking, okay, what is in the empty set but not in the other set? Well, there's nothing in the empty set to begin with, so the answer has to be the empty set itself. Does that make sense? Okay, all right. So now we are going to move on and talk about some other notations. I'm going back to the one that I just skipped. Which one is that? That right, this one here. Okay, so the rectangle portion is telling you what I'm defining. Okay, so this little bar here, and we have an E over here and a P of E over here. What does that represent? Okay, so I'm using the other symbols that we have already um, defined to look at this one. So this one is basically saying for everything in the entire universe, that thing is in this notation or the set that is generated by this notation if and only if P of E is true. Then you go like, why do we need that notation? Because sometimes we need to represent membership of a set that has an infinite number of elements. In other words, it would not be possible for me to use open brace and then just enumerate every single element in the set because there's an infinite number of elements in the set. So in those cases, I would need to rely on this particular symbol. So I use an example here. Okay, so I can just put it over here. So let's just say that I want to talk about the set of all even integers. Okay, are we good? At least the concept. I want to describe the membership of the set of all even integers. So how would we do it? So the answer to that question is we use the open brace here, and then we just use E or I or whatever. Okay, this is really just saying, you know, this is the variable that we are going to evaluate for everything in the entire universe. So the first thing we need is we need E to be in the set of all integers because anything that is not an integer, I'm not even interested. Okay, I don't care. All right. And then the second thing we also need, okay, so we use a conjunction in this case. We basically say, okay, if E is an integer, then we also need to specify the following. We also need, in this case, I'm going to switch to, well, let's not do that. So I'm going to use mod here. Since I said we want even numbers, so we need E mod 2 to be a 0. So that's going to be the second condition in the conjunction. So now this notation is giving me the set of all even integers. Are we okay so far? All right. It means, okay, so what is this? Okay, let's just say that this is E. Let's not use uppercase E, but I don't want to use the same name. So we'll give it a funky name. We'll call this Z. No, that's already used. We'll just call this Y, whatever. Okay. So we are defining Y to be this set. Okay. So what this means is for every E in the entire universe, So I'm borrowing my own notation over here. E is in Y if and only if um, E is in Z, it's an integer, and E mod 2 is 0. I'm just matching parentheses here. I'm too spoiled by the editor. I'm missing one. Okay. So these two definitions are exactly the same. They're both defining the set Y as the set of all even integers. Are we okay so far? Okay. So the important part here is which part is the same. This expression is the same as exactly this expression here. So it's really just a matter of notation. If you want to define an ad hoc set, which means it doesn't have a name, the first notation is better, okay? Because this allows you to essentially use an quote unquote anonymous function to define a set. You don't have to give the function itself a name. The second one, it works too, but you need to give it a name because there's no other way to associate the set that you're talking about and associate it with the condition of the membership. Is that okay? So it's really just a uh, notational preference. Some people really like the first one, and some people like the second one because it is actually closer to what it means. The first one is just easier to read. And if you want to, kind of figure out what the bar can, how to say the bar thing, it is usually called such that. Okay. In other words, this is basically saying um, every member of Y is an E such that E is an element of the set of integers and E mod 2 equals to 0. So the vertical bar can usually be mapped to the phrase such that. Yep. Possibly, but I'm used to the bar, so but if you use a colon, it's fine too. Yep. Ah, okay, very good. So it's good when classes kind of mesh, right? They can kind of we overlap in terms of concept. Yep. So we still have about 8 minutes to go. So let me ask you this question because this is just curiosity on my part. Um, when you took Calc 1 for people who have taken Math 400, and that's the majority of this class, I checked. Um, did they talk about the delta epsilon thing briefly? Okay. Well, but it is a really important concept, right? Yeah. So the delta epsilon concept is the application of quantifiers. You cannot understand delta epsilon without understanding um, quantifiers first. So later on, we are going to use that concept too, something that is like delta epsilon, because we also have to deal with limits in this class. Okay, not quite the same kind of limit that you're dealing with calculus, because that's continuous math. In this class here, we deal with discrete math, which means it is not continuous. But just because the math is not continuous does not mean that we don't have to deal with uh, limits. So we'll deal with that here later on. All right, so we are close to getting this all done. Okay. All right, so this bar x bar symbol is what I use to so this is what I use to represent cardinality, which is kind of the same thing as size of. Okay, it is telling me the number of elements of the set X. Okay, so bar is cardinality. Okay, so let me ask you this question. What do you think is this? It's the num it's yeah, let's call it as it is, okay? It's the number of elements of the set of all integers. They go like, well, that's kind of silly. There's an infinite number of integers, right? What about this? Okay, and by the way, this funky looking n is the set of all natural numbers. Natural numbers are basically 0, 1, 2, 3, 4, and so on. It cannot be negative. Okay, is it half of that or not? Okay, it is still infinite, right? So we are looking at the number of elements or the number of integers, right? We are looking at the number of natural numbers. And how do you think these two numbers relate? So in a math class, they will say you cannot relate infinity to infinity. You just can't, okay? Yeah, because infinity is not a value that exists, and therefore you cannot compare infinity to infinity. But these two are not exactly infinity, okay? They are the number of elements in a set. What if I tell you that later on in this class, I'm giving you kind of like a preview of episode 6, okay? In this class, we are in episode 2 right now. What if I tell you they're the same? Then you go like, it is, that's wrong, okay? What about negative 2? Because negative 2 is an integer, but negative 2 is not a natural number. These two cannot possibly be the same. Well, like most answers that I give to people when people ask me a question, my typical first response, if I don't know the answer, is it depends. It buys me some time to think about it. Okay, so in this case, it depends on what do you mean by equal. Okay, so later on, after we talk about functions, okay, then we have a really peculiar way to define the equality of cardinality between two sets. Each one has an infinite number of elements, and yet we can say, yep, they're the same. Okay, what about the rational numbers? Okay, well, as it turns out, the number of rational numbers is also the same as the number of integers. You go like, what about two-dimensional space, the pixel coordinates? It still has the same cardinality. You go like, how can that possibly be the case? Because these are one-dimensional, and the number of two-dimensional values where we are using only integers for the coordinate, that's at least two-dimensional. How can a two-dimensional space has the same number of elements as a single dimensional space? Okay, so we'll get to those things later. Okay, it's actually pretty fun and to talk about. So, but this is just a preview of things that we are going to talk about. And then we have, hmm? So when you talk about the equality, then you are looking at what we call a bijection between the two sets. But when you look at it without, the equality, without comparing to the cardinality of something else, then it's just a number. It's just an integer value. But when we use the comparison to the cardinality of something else, then we have a different way of looking at it. It is defined. It is defined by can I map something from here to here, and also map something from back in a one-to-one manner. But we'll get to that. Okay, we don't have the vocabulary to describe it yet because we need to talk about functions. What is injection? What is surjection? And also what is bijection? By the time we are done with bijection, then we have the vocabulary to express that. And that's generally the case for this class, okay? This class is introducing the symbols and the terms that you need in order to pursue the upper division classes at a four-year university. In other words, I'm only introducing the ABCs. I'm only introducing the alphabets in this class. We are not writing paper. because that will be the job of the 4-year university. An upper division class will then use the symbols that we define in this class, and then use that to prove theorems. So we'll prove some theorems. I would do some, in this class, but you don't have to prove theorems in general in this class. All right, so we are running out of time. Okay, I am going to let you guys go. Wednesday is our second class, so please, 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 study, or at least kind of organize your notes, okay? Because we are going to reuse all of these symbols, okay? You know, for the foreseeable future. So that means clearing all the concepts in this class is really important. Um, Use AI, okay? Because last week I demonstrated how to use Gemini to kind of construct quizzes for yourselves. Just go ahead and do it, okay? Let Gemini, quote unquote, grade your, you know, quiz. And if you go like, okay, I'm not really sure why, this answer is wrong or why this is the correct answer, come talk to me, okay? I have another 15 minutes or so after class, so if you need to talk to me today, I have some time. Otherwise, I will see you all on Wednesday.